All right, so let's see how we can solve the Legendre equation. One more time, this is the standard format. 1 minus x squared y prime, another prime on the outside, plus lambda y equals 0, and we're looking for the domain minus 1 and 1. I'm going to expand the parentheses inside a little bit for later. So that's y prime minus x squared y prime, another derivative on the outside, plus lambda y. Again, I'm not going to distribute the external derivative yet, just for the convenience of the computation, as you'll see later. And the idea of finding a solution really follows the same idea from Bessel functions, except that with the Bessel functions, I didn't go through this process because it was more tedious. For the Legendre equation, actually, it's a little bit easier to follow. And it's, again, worthwhile to do it because it's probably useful to understand how these series formats of the solution come to be. It's not because this Legendre guy or whoever invented the method wanted to come up with some complicated formats of the solutions. But if you think about it, and if you actually follow the process, you will realize that it's essentially the best you could do when you are faced with an equation that you must solve and for which there is no obvious compact form of the solution. So there is no way to find the solution in terms of classical functions. So then the series method of solution is that instead of having a closed format, you're looking for a series, power series, because you know a large class of functions can have a power series representation. So stands the reason that it could be possible to find a solution in the format of a power series. So that means you're looking for y in the form of summation from 0 to infinity. This will end up being a polynomial, you'll see later, but for now let's think about of a series with some coefficients yet to be determined. So this is basically a shortcut for a naught plus a1x plus a2x squared and so on. The question is, can you find these coefficients so that this power series becomes a solution? So it's just basically plugging in this format and hoping you're going to find some formula for the coefficients that match the solution. Moreover, not only you need to have a solution in this format, you need two independent solutions. Remember, the goal is to find the general solution. So it's not enough to find only one of them. You need two independent ones. So with that in mind, let's actually differentiate y prime, plug it in here, and overall in the equation, and see if we can find some rules for AK. I mean, some ways to determine AK. And again, we're going to worry about convergence later, right? So for now, we have to find a formula for AK. And then we're going to worry later what conditions we need to impose to make the solution exist, right, on the interval -1 and 1. You will see that in the case of Legendre series, that actually that's actually easy. I mean, as easy as it gets, given the topic, because you have lots of freedom in choosing some of these coefficients, as you will see later. So y prime, we're going to differentiate inside the summation. So we're going to have ak kx to the k -1, so the power rule. And we need also x squared times y prime when we plug it in here. So x squared y prime, x squared times the summation, bring the x squared inside. K -1 plus 2 becomes k plus 1. All right. Inside this derivative, we're going to have the difference of these two, y prime minus x squared y prime. And let's do one more step here. So y prime summation k0 to infinity minus x squared y prime and one more derivative to take, and then plus lambda y, which is the original summation. And this should be equal to 0. Okay, let's do the last derivative. So we're going to differentiate one more time inside the summation. And we have summation from 0 to infinity, ak, k times k minus 1, x to the k minus 2. And here it's ak, k plus 1, x to the power k. You can pause and catch up. Remember, I'm assuming that you can pause at any time, so that's why I don't go too slow on this. But you should pause and retrace the computation before you move on. All right, let's see what else we can do with this. I want you to pay attention to the last two terms here and notice these summations are in agreement. We can combine them into a single one summation. The starting point of k is the same, 0. Starting power of x is again 0. So these summations can be combined into one. Furthermore, notice that the first two terms of these summations are 0. So we can start with the index from 2. When k is 0, that's 0. When k is 1, because of the second parenthesis, that's 0 again. So therefore, we can rewrite this whole summation starting from 2. This will help us to find a recurrence relation, as you'll see later. So the same thing can start from 2, because the first two terms are 0. And like I said, let's combine these two summations into one. And we can pull out x to the k. And then you have lambda ak minus, I should have left ak outside. I'll do that next time. Minus ak times k plus 1 inside the summation, and then x to the power k equals 0. Now, remember, in order to finally match these coefficients, you need to have these two summations in agreement, meaning that the first index should be the same in both of these. So this starts from 2 because that's the first non-zero term. This one starts from 0, and there's a non-zero term to begin with, but let's make a re-indexing here so that it starts from 2. Remember, we did something similar in the case of Bessel polynomials, Bessel functions. The reindex means that I'm going to start from k equals 2. And to do that, that means I have to replace k with k minus 2. So to rewrite the same summation, but with a starting index value of 2, you're going to replace k with k minus 2. Right? So k equals 0, x to the 0, 1. If k starts from 2, I need to put here k minus 2 so that the starting power is again the same. And then the two summations can be combined and then finally match the coefficients. So the first summation stays the same. And the second summation starts from 2. And let's pull the ak out. So again, k is replaced by k minus 2. So I'm going to have ak minus 2 on the outside. Instead of k, I'm going to have k minus 2. Instead of k plus 1, I'm going to have k minus 1, right? Because k minus 2 plus 1 is k minus 1. And then x k minus 2 on the outside. So this is basically how the process works. I mean, if you look carefully right now, you're just ready to figure out what the conditions on the coefficients ak you should impose to make it a solution. This will be a solution if the sum of this coefficient and this coefficient is equal to 0, right? Because you can pull out now x to the k minus 2 and then find the recurrence relation. So basically everything ends up being a summation with k minus 1 ak plus ak minus 2 lambda minus k minus 2 k minus 1. So to make this equal to 0, you basically need to make that equal to 0. So remember, not only you need to find these coefficients, you need to find two solutions in the end. And so let's write that recurrence, and then we're gonna continue with the next page here, and then write it in a slightly more convenient way, just to match it with the textbook, and then we're gonna finish up with a remark, and I think that's enough for today's lecture. Okay, so if I write that coefficient and set it equal to 0, so I have k times k minus 1 ak equals lambda, let's see, equals, let's do, yeah, if you set that equal to 0, let me actually, let me write one more time that coefficient. Okay, so k times k minus 1 ak plus ak minus 2 parenthesis k minus 1, this should be equal to 0. So normally, because in my summation k started from 2, you can basically reindex again the summation to start from 0. Okay, so you can reindex again because it's more convenient, so that k starts from 0. So that means if I start from 0, I need to replace k with k plus 2 everywhere. Okay, so k replaced by k plus 2. That means this becomes k plus 2, k plus 1, ak plus 2. Okay, and then on the right hand, and then the second term, this is ak, k minus 2 becomes k, and then k minus 1 becomes k plus 1. It doesn't really matter, basically, the starting point, but again, remember, just for standardization purposes, I suppose, it's better to have these formulas more consistent, essentially, right? I mean, for the Bessel functions, the starting point was 0 or 1. Here, the starting point is 0. Because that's more convenient for later. Remember, the starting point 2 came from differentiating twice that summations, which meant the first two terms were 0. But then you can come back and have any starting point you want. All right, so what is the recurrence relation, basically? So if I set so this should be equal to 0, right? So if I solve for ak plus 2, then this is going to be this to the right-hand side, so I can change the sign in that parenthesis over k plus 2, k plus 1, ak. All right, so solving for ak plus 2 gives you a recurrence relation. All right, so this is a recurrence relation that determines AKs provided you know A0 and A1. This is a recurrence that goes by a step of 2. So notice that in order to know one term, you need to know the previous ones. So you need to know, for instance, A0 and A1 to get to A2. I mean, you need to know A0 to get to A2, but you need to know A1 to get to A3, and so on and so forth. So this recurrence, again, will tell you what the conditions these coefficients need to satisfy so that you have basically your solution of the Legendre equation. Now, you know what I told you that in the case of Legendre equation, things are a little bit easier. And they are easier because notice that I have no restrictions on how to pick these starting points. As long as these coefficients satisfy this relation, and of course, as long as the solution is convergent, we'll worry about that later. But as long as I have this recursion, it's not that relevant in the end what's the starting point. So what is A0 or A1? And so the immediate advantage of this is that we can actually get two independent solutions rather quickly. So first of all, let's write actually a couple of terms in this recursion so that people understand, how these terms look like when you plug in some numbers. So for instance, A2, if we start with k equals 0, right? A2 will be 0 times 0 plus 1, so that's minus lambda over 2 factorial, because it's 2 times 1, A0. Then when you move to A3, that means k is equal to 1. So you have on the top 1 times 2 minus lambda over 3 times 2, right? Which is basically 3 factorial. Well, let's leave it 3 times 2. Actually, it doesn't matter if it's factorial because later on it's not going to be. And then A4 equals 2 times 3, because k is 2 in that case, divided by 4 times 3. And so on. Okay, so to find all the coefficients, notice that, I forgot here A1, right? When k is 1. So you notice that you need to find, you need to establish what A0 and A1 is first, before you get to the later ones, A2, A3, A4, and so on. Okay, one remark I want to make here, notice that if A0 is equal to 0, then all the even indexes, A2, A4, A6, and so on, are going to be equal to 0. Again, it's very easy to see why that's the case. If I start with A0, put k equals 0. If A0 is equal to 0, that means A2 is equal to 0. When you plug A2 here and make it 0, that means A4 equals 0, so on and so forth. So if A0 is equal to 0, all of these are equal to 0, all the even ones are equal to 0, and let's say A1, so let's suppose A1 is not equal to 0. Well, if A1 is not equal to 0, then all of the odd ones are not going to be equal to 0. So basically, you can find one solution in terms of the odd polynomials, odd powers, A1x plus A 3x to the power 3 plus A 5x to the power 5, and so on. On the other hand, let's say you start with A1 equals 0, then by the same reason, the odd indexes will be 0. So if A1 is 0, A3 will be 0. If A3 is 0, A5 will be 0, and so on. And then if we suppose that the A0 now is not equal to 0, then we find another solution in the form of the even powers, right? So you're going to have A0 plus A2x squared plus A4x to the power 4 and ... So my last point for today is that it's actually very easy to produce two linear independent solutions that solve the Legendre equation. You can simply, like I said, assume A0 0 and A1 not equal to 0, and that gives you one independent solution. And alternatively, you can assume A1 equals 0, and then A0 not equal to 0, and you have another solution. So by assuming only one of the first two 0 and the other not 0, you ensure you produce two independent solutions, because these two guys never overlap, right? One will contain only the odd powers. Sometimes I'm going to call it the odd polynomial later. So the odd powers, and the other one will contain only even powers. So I'm not going to talk about how we get from a series to a polynomial, but again, let's summarize briefly the main idea and the most important part to remain with after this lesson. Looking for a series solution of the Legendre equation, we are after the conclusion that the coefficients of that series should satisfy this recursion. This recursion starts, it's of order 2 basically, right? I mean, it needs the previous two values in order to come up with the next values, right? Because it jumps 2 units, right, on every index from AK to AK plus 2. So that means if you start with A naught, you can start basically with any A naught and A1 you want. But if you start with a 0 value for A naught, this ensures all the even indexes are 0. So therefore your solution will contain just odd powers. Call that solution Y1. Alternatively, because you have the freedom to plug in anything you want for A naught and A1, if you start with A1 equals 0, but A naught not equal to 0, this ensures all the odd indexes coefficients are 0, which means your solution contains only even powers. That means these two solutions are guaranteed to be independent, so therefore your general solution can be written in terms of these two series. So we can think for all practical purposes that we know how to solve the Legendre equation. The last thing to worry about before we move to the eigenfunctions and eigenvalues is to ensure the convergence. And the easiest thing to ensure convergence, as you will see, is to basically figure out which values of lambda, which types of eigenvalues, basically, will make this series actually polynomials. So you'll see that for some values of lambdas, the summation doesn't, it's not going to be infinite anymore. It's going to stop at some point because all the coefficients will be 0 after a certain index. And so if these series turn out to be polynomials, then by default they're continuous on the interval, on any interval you need for that matter, right? Because polynomials are convergence. Polynomials are convergent for any value of x, right? I mean, they're continuous, and as functions will be continuous on the interval of your interest. So that's it for today. We're going to continue later on with more in-depth analysis of the Legendre equation.